numerical in which we have changed the sampling frequency of our ADC. The new sampling frequency of ADC is now 4096 samples per second, while the value of n is again equal to 512 samples, and the processor architecture is also same, which can solve one real computation in one clock cycle. Now let's see what changes will be happened in this numerical. The first quantity, which is number of real computations per DFT operation, will remain same as we calculated in the previous example, because it just depends on n, and we have not changed the value of n, so the requirement of computations are again equal to 2.096 million computations for one DFT operation. Now let's come to the second quantity, which can be calculated by taking a ratio of fs and n. Now the new fs is 4096, while the value of n is again 512. On taking the ratio of these two numbers, we will get the answer equal to 8 DFT operations per second. So in the previous example, we were calculating only one DFT operation in 1 second, while in this numerical we are going to take 8 DFT operations in a single second. So it means we have to update the Fourier transform results more quickly. Now let's come to the third quantity, which will also remain same because the processor architecture is very similar to the previous one. Now multiply all these three numbers. So on multiplying these three numbers, we will get the final result equal to 16.769 megahertz. So in this case, we must have to use a processor having a speed of at least this frequency value. Now the question is why the processor speed has increased from the previous case. In the previous example, we were using 2 megahertz computer in order to solve one DFT operation in a single second. Now in this case, we are required to perform 8 DFT operations in a single second. So definitely we will need a higher speed computer. If we will use a 2 megahertz computer for solving 8 DFT operations in 1 second, then it would not happen. We must have to use a faster computer in order to perform the required task in real time. Now let's come to another example in which the ADC sampling frequency is 4096 samples per second and the length of DFT operation is again 512 samples. Now the processor architecture is like that it can handle one real computation in 2 clock cycles, which means that it is taking 2 clock cycles duration to solve a single real computation, and our task is to calculate the minimum processor speed in order to meet the required specifications. Now the value of real computations per DFT operation will be again equal to 2.096 million computations for one DFT operation, because we have not changed the value of n in all the three examples, and the number of DFT operation per second will also be equal to the previous example, because the value of fs is 4096 and the value of n is 512, and on taking the ratio of these two numbers we will get 8 DFT operations per second. While the third quantity, which is number of cycles per computation, it will be equal to 2, because as we discussed in the numerical statement, our processor is taking 2 cycles for one computation, so it will be equal to 2, not half. Now on multiplying these three quantities, we will get the final result equal to 33.538 megahertz. So it means that we must have to use a processor having a speed of 33.538 megahertz in order to satisfy the given requirements. Now let's conclude this lecture by discussing the fact that if the value of n is very high, then the requirement of computations will increase drastically. As we have just solved three numericals for the value of n is equal to 512 samples, if we solve the same numericals for a very high value of n like 1 million, then the requirement of computations will be in the order of 1 into 10 raised to power 12. So you can imagine that how many computations will be needed. And when we will calculate the processor speed, then we might end up with some impractical processor speeds which are not available, or in case if the processor speed is available, then it will definitely be a very costly processor. So it will increase the overall cost of our digital system. This is also not feasible. So the conclusion is the standard DFT implementation needs a lot of computations due to the n square order of computations, which definitely increase the cost of our system. So we must have to develop a mechanism or a technique which can implement the DFT for performing harmonic analysis but in an optimized manner. So any algorithm or any technique which will implement the DFT equation in a faster way or in an optimized manner will be called as the fast Fourier transform. So fast Fourier transform is just a faster way to compute DFT. So definitely it will reduce the cost of our system. So in the next lecture we will discuss how FFT can be used to perform DFT on a given time domain sequence. Until then, thank you very much and Allah Hafiz.